Hi, class. I'd like to sort of continue on with that last lecture that we had on the exponential form, because I'm going to be using, of course, the exponential form in the next lecture that I'm doing with you to derive the telegrapher's equations. And you have to understand the some notation with the exponential form because I'll be using that. Now, let me let me just write down a few things here. We know that a e to the j theta equals a times the cosine of theta plus j times a times the sine of theta, right? Everybody knows that. And so if I had cosine a e to the j omega t, right? What would that be? That would be a times the cosine of omega t plus j times a times the sine of omega t, right? Uh, now, what if I had, well, I think you can see where I'm going with this. Anyway, now what I want to do is I want to break this up because let's say that I had a times the cosine of omega t plus phi, right? How would I represent that in exponential form? I mean, that as you look at that, you're probably saying, hey, that a could be v maximum or I maximum or phi maximum, whatever. And that is a time domain waveform, isn't it? You're saying, oh, that's fantastic, but look, I've got that right up there. So I could write that out as a e to the j omega t plus phi. You're saying, look at that. That's it. That's it right there. Oh my God, no, I've got this. So I've got to like subtract off the j a sine omega t. How do I subtract that off? Here's how you subtract it off. You say this: I want the real part of that. I want just the real part of that. And that's the notation that we use to keep track of everything for our bookkeeping in the new math that you're going to learn and use for the rest of your life. That's right, because that's how we do it. This is the way that you should really start, in the future and everything else that you start to use the exponential form now. So, yeah, if I had that. Now what if instead I had something like a times the sine of omega t plus theta, right? What if I had something like that? Well, then what you do is you use the imaginary preface of a times e to the j omega t, and in this case I use theta just to differentiate that you don't have to use the same angle or whatever. Whatever the angle is, who cares? And that's just the notation that you would use. So real, imaginary, and I just wanted to point that out to you. Now, I can also break this up, couldn't I? Because as you look at this, the real of A e to the j omega t plus phi is equal to the real of A to the e j omega t times e to the j theta, or phi, excuse me. Does everyone see how that works? In other words, inside the real or imaginary brackets, the exponential function works the same way that it works in regular mathematics, right? Regular mathematics. So it breaks right apart, just like it is here. I'm adding exponents together, so really I've got that. And what will that allow me to do? That allow me to break those two things apart later on and then represent them differently. And that's what I want to do. I want to do an example problem along that regard. Now, what if I wanted to go from the imaginary to the real? And that's what I want to point out to you right now. Okay, let's just cut this off right here. And let's look at an example. For instance, let's say that I had B, think of it as a magnetic field or something, times the sine of omega t plus phi. And I wanted to change that because right now I can see that that is going to be the imaginary part, right, of e to the j omega t plus phi. Now that's the imaginary part, right? Now when you're working through problems, you can't add the imaginary to the real. You can add the imaginary, to the imaginary, and the real to the real. So you have to come up with a way that's going to allow you to switch from imaginary to real, right? And you can see that this right now is in the imaginary form of that. So how do I switch that? Well, we use this identity, and that is that the sine of theta equals the cosine of theta minus 90 degrees. Okay? So the sine of theta, right? Here'd be the sine of theta. That would be what we'd be thinking of as theta right now, equals the cosine of theta minus 90. And what is 90? You might have noticed more and more that whenever we're talking about theta up here, we usually use radians, right? Whereas in here, we're using angles a lot. But this is radians, and that's what you're going to do. So you have to start to know radians and use radians and everything too. Be the engineer. So we'll. This is and how do I make that change in here? Well, let's look. So we've got B equals the imaginary. Oops, I should have put a B in there too, right? So now I've got minus 90, and that's pi over 2, isn't it? Because I've got 2 pi and 360, so 360 divided by 4 gives me 90, and 2 pi divided by 4 gives me pi over 2. So I end up having, I'll just write it out here, the imaginary of B times e to the j omega t plus phi equals the real, right, of B times e to the j omega t plus phi minus pi over 2, right? You see how I've done that? So I've switched it from imaginary now to real. So everyone see how I switched it using the identity, the trigonometric identity over here? So everybody should be able to see how I did that. And of course, now what I can do is I can break this all up. I've got this really equaling the real part of B times e to the j omega t e to the j phi, and then e to the minus pi over 2, right? Does everyone see how I switched that all around? And now, of course, this would be the real part of that, because I put this in there, and that'd be a cosine. So if I wanted to bring this back, this would all be a cosine now, wouldn't it? Because it's now the real part, which is the cosine part, not the imaginary part, which is the sine part. And remember when we're looking at the real and the imaginary, this whole thing here is the real part of the complex number, whereas this, not the j, is the imaginary part. There's no j in there for the imaginary part. The j is just a placeholder, right? Okay, good. Now, let's get back to this. I think this pen is running out of, I've got to hit them with, like, I think it's rubbing alcohol, which of course I don't have. Why would I have rubbing alcohol? So what I want to do is a little example of adding two waveforms together. So let's just see if we can go through this and see if we get it. Of course, no, I haven't timed myself or anything like that, but I thought that I'd try to get this one done, and I'm sure that I've got the time for it. I'm sure I do. So let's say that I've got a waveform that is 5 times the cosine of omega t. And I want to add to that another waveform that is 10 times the sine of omega t, but phase shifted from omega t by 30 degrees. So basically what I'm saying is I've got two waveforms that are of the same frequency, but one is phase shifted from the other one. And I'm sending them through and adding these two waveforms together, right? And then what do I get when I add these two waveforms together out the other side? And I'll tell you right now, it's going to be a sinusoidal, I'm sure, but with maybe a different phase, right? So what I've got to do then is I have to sort of switch these around, because I want them both to be cosine so that I can work with it in the real form. This one would be real, this one would be imaginary. So I've got to turn either this one into real, or I've got to turn this one into imaginary. And I like to use real. It's probably a preference. There's probably some fantasy people out there that like to live in imaginary land, but I like to live in real land. So what I'm doing is I'm going to say that this is going to remain 5 cosine omega t. But I'm going to change this one. I'm going to change this one into 10 times the cosine of omega t minus 30 degrees, but minus pi over 2, which is going to be 90 degrees, right? So I've added that in there, and I've done that so that I can do this. I can say that this is going to be the real of 5 e to the j omega t, right? And I'm going to add to it the real part of 10 times the e to the j omega t minus 120 degrees. Now, 120 degrees, as everyone knows, is 2/3 pi, because it's 2/3 of the way to 180 degrees, right? And of course, I've still got to put my real bracket around there, right? So I've got that, like that. I hope nobody has any questions yet, right? Because I've just added these two together. So now I've got this all set up like this, and I can rewrite this. Now I've got the real part of 5e to the j omega t e to the 0 plus 10 e Oh, I'm sorry. There should be a J there, shouldn't there? I'm sorry. There's a J0. Yeah, that's fine. It doesn't really make any difference. It's still, still 1. Um, let's get back to this. So I've got 10 e to the j omega t, and then e to the minus 2 pi over 3. Does everyone see how that worked there? I hope. Let's see. I've got broke that all up. Okay, so let me just finish that. And so now I think you can see that both of these have an e to the j omega t in them, right? So let's do the real again. And let's take the e to the j omega t out, right? So if we take e to the j omega t out, then what we're left with is 5e to the j0 plus 10 e to the j minus 2 pi over 3. Right, does everyone see that? So let's break those up. 5e to the j0. How would that go? 5e to the j0. 5e to the j0. 5e to the j0. Wouldn't that just be 5 plus j0? Wouldn't that be 5 at an angle of 0 degrees? Does everyone see what I'm talking about there? So, oh, I forgot to put, yeah, I should have put a parentheses here. Sorry about that. So let's look at that now. So the real part of this, right, is going to be ej omega t, and then I'm going to do some brackets here. And this part is going to be 5 plus j0, right? Can everyone see that? E to the j0, because cosine of 0 is 1, and sine of 0 is 0, right? 1, 0. See, that's why I did it there. Plus, now let's get this one. E10 e to the minus 2 pi over 3. If I was to draw the complex plane over here, let's see where 120 degrees would be. Wouldn't 120 degrees be right about there? I hope everybody can see this. Isn't that about 120 degrees? So 120 degrees, oh wait, I'm sorry, that's minus 120 degrees, which would be down here, wouldn't it? So excuse me for that. Should I get my handy pen that I love to use out, my Correcto pen? Sure, why not? There we go. Yes, I don't know what you're talking about. I never wrote that. That's right, minus 120 degrees. So it's going to be down there. So what does that mean? That means it's going to have a negative real number and a negative imaginary number, right? I think everybody can see that. And if we do realize that this is really a 30-degree triangle here, right? 30-degree right triangle, I think everybody can work it out. What you end up getting is you get minus 5 and minus 8.66, right? So let's just add those two together. Those two imaginary or complex numbers together. Let's keep the e to the j omega t out there. But then let's add up these. Well, 5 minus 5, that gives me 0. And then 0 plus a minus 8 point, oops, I forgot the J. The minus 8.86 is 0 minus J 8.66. I think everybody can see that, right? Okay. Now, let's take this. Now I'm going to bring this back up here. We're almost done with this, thing. Now, let's break this back out again, back into its thing. So I think everybody can see what would that be? 8.66, and it's in the negative J direction. So it'd be 8.66 at either positive 270 degrees or negative 90 degrees. I'll use 270. It doesn't bother me. So I've got the real now of e to the of e to the j omega t times 8.66 e to the 3 pi over 2. Do you want to use that one? We could use minus pi over 2 as well, but I'll use a positive. I'll use a positive number there. That's fine with me. It doesn't bother me. 3 pi over 2. And so let's rewrite this now because we know it's the real and we know it's that, and we've got this. So let's put it all together. So we've got the real now. We're putting it back together of 8.66 e to the j omega t plus 3 pi over 2. And it's the real part, so we know that it's 8.66 times the cosine of omega t plus 3 pi over 2. That would be what the addition of these two waveforms would equal. Does everyone see how that works out? And of course that is, but look at this. This is a positive. Now, if we wanted to look at it, it could be minus a negative, minus 90 degrees, or it could be plus 270 degrees, however you want to look at it. Let's say it's minus 90. Then we started off with one that was right at 0 and one at minus 30, and we ended up with one, well, actually, this is 120 because when we went to both cosine, you can see that we did that. Now, so that was minus 120. So we had one that was minus 120, we had one that was 0, and we ended up with one that is plus 270. Now, if I wanted to write this out in sinusoidal form, that would be 8.66 times the sine of omega t. Because cosine minus 90 or plus 270, however you want to do it, equals the sine, right? So I could say to a person who asked me what those two added together were, I could say that it was this, or I could say that it was this. Either one. All right. Does everyone understand how all of those things go together and where we use the real and the imaginary? And I'm gonna because you have to, because my next lecture is going to use those. So I hope that this is just really a review of the exponential form, and you've used it all the time and you're so comfortable with it. Okay, I'll see you on the next lecture.